Current electricity. Lesson 13. Simple voltaic cells. 162. Flow of currents. It has been already mentioned in Lesson 4 how electricity flows away from a charged body through any conducting substance, such as a wire or a wetted string. If, by any arrangement, electricity could be supplied to the body just as fast as it flowed away, a continuous current would be produced. Such a current always flows through a conducting wire if the ends are kept at different electric potentials. In like manner, a current of heat flows through a rod of metal if the ends are kept at different temperatures, the flow being always from the high temperature to the lower. No exact evidence exists as to the direction in which the current in a wire really flows. It is convenient to regard the electricity as flowing from positive to negative, or in other words, the natural direction of an electric current is from the high potential to the low. It is obvious that such a flow tends to bring both to one level of potential. In order that a continuous flow may be kept up, there must be a circuit provided. The current has sometimes been regarded as a double transfer of positive electricity in one direction and of negative electricity in the opposite direction. The only evidence to support this very unnecessary supposition is the fact that, in the decomposition of liquids by the current, some of the elements are liberated at the place where the current enters, while others are liberated at the place where it leaves the liquid. The quantity of electricity conveyed by a current is proportional to the current and to the time that it continues to flow. The practical unit of current is called the ampere. The quantity of electricity conveyed by a current of 1 ampere in 1 second is called 1 ampere-second or 1 coulomb. 1 ampere-hour equals 3,600 coulombs. If C represents the current in amperes, T represents the time in seconds, and Q represents the quantity of electricity in coulombs, the relationship is expressed as Q equals C multiplied by T. Example: if a current of 80 amperes flows for 15 minutes, the total quantity of electricity conveyed will be 80 multiplied by 15 multiplied by 60 equals 72,000 coulombs. This is equivalent to 20 ampere hours. Currents are called continuous if they flow without stopping in one direction. They are called alternate currents if they continually reverse direction in a regular periodic manner, flowing first in one direction around the circuit and then in the other. Continuous currents of electricity, such as we have described, are produced by voltaic cells and batteries of such cells, or else by dynamos driven by power, though there are other sources of currents hereafter to be mentioned. Alternate currents are produced by special alternate current dynamos or alternators, which are treated separately in Article 470. 163. Discoveries of Galvani and of Volta. The discovery of electric currents originated with Galvani, a physician of Bologna, who, around the year 1786, made a series of curious and important observations upon the convulsive motions produced by the return shock, as described in Article 29, and other electric discharges upon a frog's leg. He discovered that it was not necessary to use an electric machine to produce these effects. A similar convulsive motion was observed in the frog's leg when two dissimilar metals, such as iron and copper, were placed in contact with a nerve and a muscle respectively, and then brought into contact with each other. Galvani imagined this action was due to electricity generated by the frog's leg itself. However, Volta, a professor at the University of Pavia, proved that the electricity arose not from the muscle or nerve, but from the contact of the dissimilar metals. When two metals are placed in contact in the air, one becomes positive and the other negative, as explained at the end of Lesson 7, though the charges are very feeble. Volta proved their reality by two distinct methods. 64. The Voltaic Pile. The second of Volta's proofs was less direct but even more convincing. It consisted of showing that when a number of such contacts of dissimilar metals could be arranged to add their electrical effects together, those effects were more powerful in proportion to the number of contacts. With this view, Volta constructed the apparatus known as the Voltaic Pile, named in honor of the discoverer. It is made by placing a pair of discs of zinc and copper in contact, laying on the copper disc a piece of flannel or blotting paper moistened with brine, then adding another pair of discs of zinc and copper, and so on. Each pair of discs in the pile is separated by a moist conductor. Such a pile, if composed of a sufficient number of pairs of discs, produces electricity strong enough to give a perceptible shock when the top and bottom discs, or wires connected with them, are touched simultaneously with moist fingers. When a single pair of metals is placed in contact, one becomes positively electrical to a small extent, and the other negatively electrical. In other words, there is a small difference of electric potential, see Article 265, between them. But when multiple pairs are arranged in series with moist conductors in between, the difference of potential between the first zinc and the last copper disc increases in proportion to the number of pairs, as all the small differences of potential are added together. Nadas 165, the crown of cups. Another combination devised by Volta was the couronne de tasses, or crown of cups. This consisted of a number of cups filled with either brine or dilute acid. A number of compound strips, half zinc and half copper, were arranged so that the zinc portion of one strip dipped into one cup and the copper portion dipped into the next. The difference of potential between the first and last cups is proportional to the number of pairs of metal strips. This arrangement, though not ideal for practical use, is powerful enough to ring an electric bell when the wires are joined to the first zinc strip and the last copper strip. The electrical action of these combinations is best understood by studying the phenomena of a single cup or cell. 166. Simple voltaic cell. Place in a glass jar some water with a small amount of sulfuric acid or any other oxidizing acid added to it. Place in the jar 2 clean strips, one of zinc and one of copper, positioned separately from each other. This arrangement forms a simple voltaic cell capable of supplying a continuous flow of electricity through a wire connected to the 2 strips. When the current flows, the zinc strip gradually dissolves, as its consumption provides the energy necessary to drive the current through the cell and the connected wire. The cell can be likened to a chemical furnace, where zinc serves as the fuel, the acid as the oxidizing agent, and the copper acts merely as a conductor to collect the current without participating chemically. Before connecting the strips with a wire, no significant difference in potential between the copper and zinc can be measured using an electrometer. This is because the electrometer measures the potential at a point in the air or the oxidizing medium outside the metals, not the potentials of the metals themselves. The zinc strip has a higher tendency to dissolve, with its surface at approximately 0.86 volts above the surrounding oxidizing medium. In contrast, the copper strip has a potential of 0.81 volts above the medium, indicating a weaker tendency to oxidize. Thus, a latent potential difference of about 1.05 volts exists between the zinc and copper strips. This potential difference does not produce a current until the strips are connected by a wire or made to touch. Once connected, electricity flows through the acid from the zinc to the copper, as shown by the arrows in the diagram, and returns through the metal circuit from copper to zinc. Simultaneously, a small amount of zinc dissolves into the solution, releasing its stored energy as its atoms react with the acid. The energy released by the zinc drives electricity through the acid toward the copper strip and then through the wire circuit back to the zinc strip. The copper strip, where the current starts its journey through the external circuit, is referred to as the positive pole, while the zinc strip is the negative pole. If 2 copper wires are attached to the tops of the 2 strips, no current flows as long as the wires remain unconnected. However, the wire attached to the zinc will be negative, and the wire attached to the copper will be positive, reflecting the zinc's continued tendency to oxidize and drive electricity through the cell from zinc to copper. This is indicated by the positive and negative signs in the diagram. This distribution of potentials once led some to believe that the junction of the zinc with the copper wire was the starting point of the current. However, the true starting point is at the surface of the zinc within the cell, where the chemical reaction generates energy. Electrochemical actions within the liquid continually renew the potential difference between the strips. At the same time, small bubbles of hydrogen gas appear on the copper strip. Both the dissolution of zinc and the generation of hydrogen bubbles persist as long as the circuit remains complete. The metallic zinc can be considered a reservoir of energy. If burned in air or oxygen, zinc releases this energy as heat. In the quiet chemical reactions of the cell, however, zinc's energy is released as electric energy rather than heat. Any heat produced in the cell represents inefficiency, as the intended output is electric energy driven by the cell's electromotive force. 167. Effects produced by current. The current itself cannot be seen to flow through the wire circuit. Hence, to prove that any particular cell or combination produces a current requires a knowledge of some of the effects which currents can produce. These are of various kinds. A current flowing through a thin wire will heat it. Flowing near a magnetic needle, it will cause the needle to turn aside. Flowing through water and other liquids, it decomposes them. And lastly, flowing through the living body or any sensitive portion of it, it produces certain sensations. These effects, thermal, magnetic, chemical, and physiological, will be considered in special lessons. 168. Voltaic battery. If a number of such simple cells are united in series, the zinc plate of one is joined to the copper plate of the next, and so on, creating a greater difference of potentials between the copper pole at one end of the series and the zinc pole at the other end. Hence, when the two poles are joined by a wire, there will be a more powerful flow of electricity than one cell would cause. Such a combination of voltaic cells is called a voltaic battery. There are many ways of grouping a battery of cells, but two need special notice. If the cells are joined up in one row, as shown in figure 98, they are said to be in series. Electricians often represent a cell by a symbol in which a short, thick line stands for the zinc and a longer, thin line for the copper, or carbon. Thus, figure 98 represents 4 cells joined in series. So joined, they do not yield more current, more amperes, than a single cell would yield, but they yield that current with a 4-fold electromotive force, that is, with more volts of pressure. The other chief way of grouping cells is to join all the zincs together and all the coppers or carbons together. They are then said to be in parallel or joined for quantity. So joined, they have no greater electromotive force than one cell. The zincs act like one big zinc and the coppers act like one big copper, but they will yield more current. Figure 99 shows the 4 cells grouped in parallel. Thus grouped, they would yield a current 4 times as great as one cell alone would yield. 169. Electromotive force. The term electromotive force is employed to denote which moves or tends to move electricity from one place to another. For brevity, we sometimes write it as EMF. In this particular case, it is obviously the result of the difference of potential and proportional to it. Just as in water pipes, a difference of level produces a pressure, and the pressure produces a flow as soon as the tap is turned on, so a difference of potential produces electromotive force, and electromotive force sets up a current as soon as a circuit is completed for the electricity to flow through. Electromotive force, therefore, may often be conveniently expressed as a difference of potential and vice versa, but the student must not forget the distinction. The unit in which electromotive force is measured is termed the volt, see Article 354. The terms pressure and voltage are sometimes used for difference of potential or electromotive force. 170. Volta's laws. Volta showed, see Article 79, that the difference of potential between two metals in contact depended merely on what metals they were, not on their size nor on the amount of surface in contact. He also showed that when a number of metals touched one another, the difference of potential between the first and last of the row is the same as if they touched one another directly. A quantitative illustration from the researches of Ayrton and Perry was given in Article 80. But the case of a series of cells is different from that of a mere row of metals in contact. If, in the row of cells, the zincs and coppers are all arranged in one order, so that all of them set up electromotive forces in the same direction, the total electromotive force of the series will be equal to the electromotive force of one cell multiplied by the number of cells. Hitherto, we have spoken only of zinc and copper as the materials for a cell, but cells may be made of any two metals. The effective electromotive force of a cell depends on the difference between the two. If zinc were used for both metals in a cell, it would give no current, for each plate would be trying to dissolve and to throw a current across to the other with equal tendency. That cell will have the greatest electromotive force, or be the most intense, in which those materials are used that have the greatest difference in their tendency to combine chemically with the acid, or which are widest apart on the contact series given in Article 80. Zinc and copper are convenient in this respect, and zinc and silver would be better, but for the expense. For more powerful batteries, a zinc-platinum or a zinc-carbon combination is preferable. That plate or piece of metal in a cell by which the current enters the liquid is called the anode. It is that plate which dissolves away. The plate or piece of metal by which the current leaves the cell is called the cathode. It is not dissolved, and in some cases receives a deposit on its surface. Resistance. The same electromotive force does not, however, always produce a current of the same strength. The amount of current depends not only on the force tending to drive the electricity around the circuit, but also on the resistance it encounters and must overcome during its flow. If the cells are partly choked with sand or sawdust, as is sometimes done in so-called sawdust batteries to prevent spilling, or if the wire provided to complete the circuit is very long or very thin, the action will be partly impeded and the current will be weaker even though the electromotive force remains unchanged. The analogy of water pipes is again helpful. The pressure that forces water through pipes depends on the difference in level between the cistern from which the water flows and the tap to which it flows. However, the amount of water flowing through depends not on pressure alone, but also on the resistance encountered. For if the pipe is very thin or clogged with sand or sawdust, water will only flow through slowly. Similarly, metals generally conduct electricity well, with low resistance. However, metal wires must not be too thin or too long, as they will resist too much and permit only a feeble current to pass through. Liquids in the cell do not conduct nearly as well as metals, and different liquids exhibit varying resistances. Pure water conducts electricity so poorly that it acts as an almost perfect insulator for the feeble electricity of a voltaic battery, though it is a fair conductor for the high potential electricity of frictional machines. Dissolved salts such as salt or saltpeter in water are good conductors, as are dilute acids, though strong sulfuric acid is a poor conductor. The resistance of the liquid in the cells can be reduced by using larger metal plates and positioning them closer together. Gases are poor conductors, and the bubbles of hydrogen gas produced at the copper plate during cell action further increase the internal resistance by reducing the effective surface area of the plates. Chemical actions. The production of an electric current by a voltaic cell is always accompanied by chemical actions within the cell. At least one of the metals must be readily oxidizable, and the liquid must be capable of acting on the metal. It is observed that metals such as zinc, which are at the electropositive end of the contact series, see Article 80, are oxidizable, while electronegative substances such as copper, silver, gold, platinum, and graphite are less so. The latter three, in particular, resist the action of all acids. There is no conclusive proof that their electrical behavior is caused by their chemical behavior or vice versa. It is likely that both are the result of a common underlying cause, see Articles 80 and 480. A piece of pure zinc, when dipped alone into dilute sulfuric acid, is not attacked by the liquid. However, commercial zinc, which contains impurities, dissolves in dilute sulfuric acid, producing a large quantity of hydrogen gas bubbles from the metal's surface. Sulfuric acid is a complex substance, with each molecule composed of a group of atoms, 2 of hydrogen, 1 of sulfur, and 4 of oxygen. The chemical reaction by which zinc combines with the acid radical, displacing hydrogen, can be expressed as follows. 1 atom of zinc reacts with 1 molecule of sulfuric acid composed of 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. This reaction produces one molecule of zinc sulfate composed of one atom of zinc, one atom of sulfur, and four atoms of oxygen, and one molecule of hydrogen gas composed of two atoms of hydrogen. In symbolic form, zinc plus sulfuric acid produces zinc sulfate and hydrogen gas. The sulfate of zinc produced in this reaction. The sulfate of zinc created during the reaction remains dissolved in the liquid. When a plate of pure zinc and a plate of a less easily oxidizable metal, such as copper, platinum, or carbon, especially the hard carbon from gas retorts, are placed side by side in the acid, no significant chemical action occurs unless the circuit is completed by connecting the two plates with a wire or by making them touch. Once the circuit is completed, a current flows and chemical reactions begin. The zinc dissolves into the acid, and hydrogen gas is released in streams of bubbles. Interestingly, these hydrogen bubbles are not evolved at the zinc plate or throughout the liquid, but rather at the surface of the copper plate, or carbon plate if carbon is used. This apparent transfer of hydrogen gas through the liquid from the zinc plate to the copper plate is notable. Grothus's ingenious theory explains this phenomenon, as detailed in lesson Edsel-Cephine on electrochemistry. The chemical reactions continue as long as the current flows. The amount of zinc consumed in each cell is proportional to the quantity of electricity passing through the circuit while the battery operates. Similarly, the amount of hydrogen gas evolved is proportional to the zinc consumed and the current. Once the acid has dissolved the zinc, it is transformed into zinc sulfate and is no longer able to act as a solvent. As a result, the battery stops functioning when either the zinc is entirely consumed or the acid is fully converted to zinc sulfate. Large zinc plates last longer, but the acid needs frequent renewal, with the spent liquid being discarded. Local action. When the circuit is not closed, the current cannot flow, and there should be no chemical reaction while the battery is inactive. However, impure commercial zinc continues to dissolve in the acid and release hydrogen gas. This phenomenon, known as local action, arises due to impurities in the zinc, such as iron, arsenic, and other metals. For example, a particle of iron on the zinc surface acts like the copper plate in a battery relative to nearby zinc particles. This creates a local difference in potential, initiating a localized or parasitic current from the zinc particles through the acid to the iron particle. This process causes continuous zinc wastage, regardless of whether the battery circuit is open or closed. Ordinary commercial zinc is attacked by acid due to local action caused by its impurities. To prevent this waste, the zinc plates are often amalgamated with mercury. The surface is cleaned by dipping it into acid, after which a few drops of mercury are poured over it and rubbed in with a cloth. This forms a pasty amalgam of zinc and mercury. Impurities like iron do not dissolve in mercury and are carried away by hydrogen bubbles. As the zinc dissolves in the acid, the mercury amalgam continuously exposes fresh zinc to the liquid, maintaining a clean, bright surface. A more modern method involves adding approximately 4% mercury to molten zinc before it is cast into plates or rods. Properly amalgamated zinc plates should not release hydrogen bubbles when the circuit is open. However, there is still a minor amount of wasteful local action during battery operation. Jacobi observed that for every 1 part of hydrogen released at the cathode, 33.6 parts of zinc dissolved at the anode, instead of the expected 32.5 parts, which corresponds to the chemical equivalent of hydrogen. Simple laws of chemical action in the cell. We will conclude this section by enumerating the 2 simple laws of chemical action in the cell. The amount of chemical action in the cell is proportional to the quantity of electricity that passes through it. This means that the chemical action is directly proportional to the current while it flows. Specifically, a current of 1 ampere flowing through the cell for 1 second will cause 0.000336698 grams, or 1/2957th of a gram of zinc to dissolve in the acid, and will liberate 0.000010384 grams, or 1/96,202nd of a gram, of hydrogen. 2. The amount of chemical action is equal in each cell of a battery consisting of cells joined in series. The first of these laws, discovered by Faraday, was thought to disprove Volta's contact theory. Faraday foresaw that the principle of the conservation of energy would rule out the possibility of a mere contact force furnishing a continuous supply of current. He therefore attributed the current to the chemical actions, which are proportional in quantity to the current. How the views of Volta and Faraday can be reconciled has been indicated in earlier paragraphs. These laws, however, only concern the useful chemical action and do not account for the waste due to local actions caused by parasitic currents arising from impurities.